So today we have Noam Lifshitz from Hebrew University. And he's gonna talk about product free sets in the alternating group. Yeah.
So do it using my tablet.
Mm-hmm.
Okay. 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 So we'll talk about product free sets, and the main tool is going to be hypercontractivity for global functions. Okay. So the problem about product free sets is in extremal combinatorics, where we want to figure out how large can a set be given some restrictions, and we call a set extremal if it is the largest set satisfying the restrictions. And one example of such a theorem is the Erdős-Corrado theorem that talks about intersecting families. So a family is intersecting if the intersection of each two sets in the family is non-empty. And one example of an intersecting family is the dictator. So we can choose some element of 1 up to n and take all the sets that contain this element. And this is an example of an intersecting family, because if we take two sets, then two sets that contain I, then their intersection must also contain I, so it's non-empty. And the Erdős-Corrado theorem says that the extremal intersecting families are the dictator. So the trivial example of an intersecting family is actually the largest one. Okay, so that's the philosophy of Erdős-Corrado type problems. Instead of coming up with interesting example, we can just choose the trivial ones when we try to come up with large sets that satisfy certain restrictions. Okay. And this Erdős-Corrado theorem, it started a whole field of Erdős-Corrado type problems, where we are given an extremal problem in some set X, and we have some candidates of extremal examples. We have some dictators, and we want to show that the extremal set that satisfies the restriction is a dictator. Okay, so where did the name dictator come from? So if the dictator is the family of all sets that contain a single element, you can think of it as that this single element decides whether the set belongs to the family or not. If the elements belong to the set, then we put it in the family, and if it doesn't, then we put it out of the family. So there is a single element that decides what's going on. And there is a theory of social choice that's about elections. And you can think about elections between two alternatives, pizza and ice cream. And the dictator function is the function where we listen only to one guy. And you can also think about a more generalized version of a dictator, which is a junta, where we have a small number of variables that determine the outcome of the elections. So instead of having just one, we can have three people that determine the outcome of the election. Okay. And it turns out that this notion of juntas is not only relevant in the social choice world, when we talk about elections, it's also relevant in for Erdős-Corrado type problems. So what does it mean that a family of sets is a junta? It means that if we want to determine whether a set belongs to the family, we only need to check its intersection with a set A union J. So if we want to check whether a set belongs to the family, we need to check its intersection with a given set of vertices. So if J consists of one element, this is the dictator. We only need to check the intersection of A with a single element to know whether it belongs to the dictator or not. And it turns out that you can use this notion of a junta to solve Erdős-Corrado type problems. And okay, so yeah, so the case of interest is the case where J is of constant size. This is this generalizes the notion of a dictator. And what Dinur and Friedgut showed is that not only the largest intersecting family is a dictator, but actually every intersecting family is essentially contained in an intersecting junta. So the only way to construct an intersecting family is to take an intersecting junta and then add a little bit, and then remove elements from the intersecting junta. Because if you have an intersecting family, you can always remove element and it will stay intersecting. And then you are allowed to add only a little bit of elements, a small amount of elements outside of the junta. And that's the structure of every intersecting family. So it's basically, you can think of it as a classification of all the intersecting families, and that they are all almost juntas, almost contained in juntas. So that was a nice result. And what we showed is that not only is that the junta approximation by junta results are nice by themselves, but you can actually use approximation by juntas to solve Erdős-Corrado type problems. So you can use this junta structure to determine the actual extremal example. Okay, so what do you have so far? We talked about what are extremal problems, which I assume most of you already knew. So how large can a set be given restrictions? And we talked about the Erdős-Corrado theorem. This is the largest intersecting family is a dictator. And we talked about Erdős-Corrado type theorems, which are extremal problems with extremal dictators. And also we talked about the junta method, which uses this notion of juntas and approximation by juntas to solve Erdős-Corrado type problems. Okay, and now we'll switch to a different topic, which looks unrelated. It looks like it comes from additive combinatorics or group theory even. And it turns out that it's actually an Erdős-Corrado type problem, and that's the problem of product-free sets. Okay, so what are product-free sets? So group theorists, they like to study the problem about subgroups. So subgroups are sets that are closed under multiplication. For each two elements in the set, the product is inside the set. And we will study the notion of product-free sets. So that means that for all two elements in the set, the product is not in the set. So that's like the opposite notion. And from the point of view of extremal combinatorics, it's very natural to ask what is the largest product-free set. So we have a product-free set. The product of two elements in the set is outside of the set. And what Gowers asked is, what is the largest product-free set? So, for example, you can consider the case where the group question is the symmetric group. So, can anyone tell me what is the largest size of a product-free set in the symmetric group? Yeah, did someone write in the chat? No, okay. Yeah. No.
Okay, yeah. The coset of the alternating group?
Yeah, exactly. Yeah, so if you take the odd permutations, the product of two odd permutations is even. So it's a product free set because for each two odd permutations, the product is even. And on the other hand, if we take if A is product free, and G is in A, then A and GA.
Noam, I think you're blocking your mic. So,
yeah.
So
if A is product free and G is in A, then A and GA, their intersection is empty because it's a product free set. And that means, and GA is the same size as A, so this implies that the density of A is at most n factorial over 2, and therefore the odd permutations are indeed the extremal product free set. Yeah. Okay. Okay, so we solved this problem in the symmetric group. That was easy. And now the question is, the next question is what happens if we restrict ourselves to the alternating group and ask for the largest product free sets in the alternating group. And it also makes a lot of sense from a group theoretic perspective because it's a finite simple group. And Ben Green has a list of 100 favorite open problems, and this is number 4 in that list. And for us, the appeal is actually that the conjecture extremal set for this problem, it actually looks like a dictator. So even though it's like a problem from group theory or from additive combinatorics, it's actually an Erdős-Corrado type problem because the extremal example looks like a dictator. Okay, so let's okay, first I'll show this silly joke and then okay, and then move on. Okay, and okay, so what are dictators in the alternating group? Yeah, so what does it mean that a family is in the dictator? It means that if I want to check whether an element belongs to the family, I only need to check one coordinate. So if I have a set of permutations, for it to be a dictator, it means that in order to decide whether a permutation belongs to the dictator, we only need to check the value of the permutation on a single coordinate. So these give us this example of dictators. So the set of all permutations that send a single element to a single set. And these are the dictators in the alternating group. But I told you that dictators are product free, and they are in fact external product free sets. But actually, if you define it like that, they are not product free. And the reason is that if we can make sure we can find dictator, we can find sigma and tau, and make sure that sigma of 1 is in I and also tau of 1 is in I. But we can also make sure that tau of sigma 1 is also in I. So we can make all of these conditions hold simultaneously, and then this implies that sigma and tau and also tau sigma are all in the dictator, and therefore the dictator isn't product free. Okay, but it turns out that we can modify the dictator a little bit, and then it will be product free. So how do we do that? We take all the elements. Okay, so the dictator again is like the set of all permutations that send a given element I to a given set I, and then we can modify it and make it product free by adding an extra condition, the condition that sigma of the set I is contained in the complement of I. So sigma I and I are disjoint. And this makes FII product free. So why is that? suppose that sigma is in FII. This means that sigma of 1 is in I. And then if tau is in FII, this means that tau of I is in I complement. And therefore, if we take tau sigma of 1, this is not going to be in I. So this means that tau sigma is not in FII. Okay. So this set is indeed product free. And Eberhard and also Crane, they conjectured that this is the extremal product free set. So you can choose a proper set I, a proper size for a set I, it doesn't matter which set you choose. And the proper size is roughly root n. So this extra condition that sigma I is disjoint from I, when I is of size root n, this happens essentially for free. You only need to be slightly lucky. It happens with a constant probability when I is of size root n. So, yeah. So I is in root n, and the probability that sigma I is contained in I bar in the complement of I, this is a constant. So this is, yeah, so this is a set contained in a dictator, and you can sort of see the relation to the Erdős-Corrado theorem. And okay, so what is known about this problem? So Gowers showed that the extremal product free set in the alternating group has small density. It has density at most n to the minus 1/3. So size at most n minus 1/3 times n factorial. And Eberhard later showed the right order of magnitude up to polylogarithmic factors. So we showed log n to the 7 times n to the minus 1/2 times n factorial. And we solved the problem completely, and we showed that the conjecture is correct, and the extremal product free set in AN is indeed a product free dictator. So it's a dictator that was so a set obtained from a dictator by messing with it a little bit to make it product free. And this is indeed the extremal example. Okay, so are there any questions so far? Okay.
What's O tilde here?
O tilde, so it's log n to the 7.
Oh, okay.
Okay. Okay, so so let's start by explaining how Gowers proof worked. Okay, so for simplicity, so we can talk about Cayley graph without having to talk about a directed Cayley graph. Let's assume that the product free set that we care about satisfy this condition, that it's equal to A inverse, and then we can comfortably talk about Cayley graphs. Then the basic observation is that A is an independent set inside the Cayley graph that has A as a set of generators. So in the Cayley graph that has A as a set of generators, B is a neighbor of AB for all A in A. And then A, an edge, so an edge in A corresponds to so an edge A1, A2 in A corresponds to A1, A equal to A2 with A1, A, and A2 all in A. So A1, A2, and A1, A, and and A1, A2. A1, yeah, so A1A equal to A2, yeah, and the A1A and A2 are all in A, yeah, that's correct, okay. Yeah, so it corresponds to an edge. So an edge inside A in the Cayley graph that has A as a set of generators. So A plays two roles here. It's also like a set of generators and also the independent set. And basically we're looking for upper bounds on independent sets in Cayley graphs. And what Gowers showed is that we have a mixing property, which means that, and the mixing properties tells us that this Cayley graph behaves like a random graph. So how does it behave like a random graph? If we have two large sets in our group, then the number of edges between B and C behaves the same like a random graph of the same density. So the number of edges between B and C is like the product of the sizes of the sets divided by G. And this in particular implies that if we plug in A as B and C, then A can't be independent because A must contain sets, must contain edges. It must contain, in fact, many edges, as many as a random set. So that was like Gowers' idea. And to show that to show this pseudorandomness properties, he used second eigenvalues and representation theory. But in fact, it turns out that there are like other technologies that are sometimes better for showing mixing and pseudorandomness inside graphs. So what are the other ways to show mixing? So Gowers' approach was the second eigenvalue method. For those who know it, he used the trace method and representation theory to upper bound the second eigenvalue. But it turns out there are more, there are other technologies like hypercontractivity that gives you stronger mixing properties. But it turns out that hypercontractivity only holds in some domains. And what people came up with is for these domains where hypercontractivity is not relevant, they came up with the notion of reverse hypercontractivity, which is which captures some more spaces, but it's still not what we want. And we had to come up with a new notion called hypercontractivity for global functions. And that's, I guess, the title of the talk, which is this new way of showing mixing. Okay, so let's summarize things a little bit. So yeah, so hypercontractivity is a central tool on the Boolean cube. If you look at the theory of analysis of Boolean functions, a huge part of it is based on the hypercontractive theorem. And it turns out that if you try to generalize it in a straightforward way to the symmetric group, so people did it actually, but the generalizations are not very effective. And the reason for that is that there are small dictators. And it turns out that small dictators ruin hypercontractivity, or at least effective versions of it. And basically for the same reason that the largest product free set is a dictator, dictator have the worst mixing properties. And we came up with this new notion of global sets that are sets that are not dictatorial, that are far from all the dictators, and show that you can prove hypercontractivity this better notion of mixing, but only for the sets that do not look like dictators. So you have the dictators that have bad mixing, but if you have any other set, you have a better mixing, and then you can get a better bound on the largest size of a product free sets. So these are like how the ideas fit in. So you have when you have hypercontractivity, you have better mixing, and therefore the dictators that have the worst mixing are extremal as product free sets. And it turns out that hypercontractivity for global functions, it has various other applications that I want to get into. And instead, we'll talk a little bit about hypercontractivity and what it is. So in order to describe it, we define the noise operator. So we have this paddle here. This paddle corresponds to the Boolean cube. And given an element in the cube, we are going to define a neighborhood and row X of elements that are close to X. And this, after defining this neighborhood, we will be able to define this noise operator that's defined by taking expectation over Y. So we choose Y randomly out of this small neighborhood and take the expectation. So this is like a smoothing operator. Given X, we smooth the function out by taking its expectation over a small neighborhood around X. Okay, so let's define it formally. So how do we get this small neighborhood? We have this row here that you can think of as 1 minus epsilon. And we start also with this, and the given X in the cube, let's say this X. We choose this noisy version of X by remembering what X was with probability row. So with probability row, we remembered what X was, and with probability 1 minus row, we forgot it. And then we can resample it and get a vector Y that's close to X. So with probability row, we keep the vector the same, and with probability 1 minus row, we resample it. And then the noise operator is defined by taking T row F of X. So like in the picture, we define this small neighborhood of elements that are close to X by this noisy process, and then we can take the expectation of F on Y chosen according to this process, that each coordinate, we kept it the same with this probability row, probability 1 minus row, we resampled it. Okay, so so small set expansion is a property of the noise operator that's a sort of intuitive way to think about hypercontractivity. It's like a main consequence of it. So what is small set expansion? Small set expansion is about a random walk where we are given a small set A. So A here is not like the same thing as before of this small neighborhood. Now A is an arbitrary small set. And small set expansion tells us that if we take a uniformly random element in the small set and then apply a step of the random walk, then we leave the set with high probability. And the Kankali lineal small set expansion theorem tells us that if we take the noisy, so the noise operator corresponds to this random walk, where we remember each coordinate with probability rho and with probability 1 minus rho, we resample it. And the small set expansion theorem tells us that this random walk is a small set expander. So if we start with a small set A of small density and take a random element of A and take a step of the random walk, then we leave A with high probability. Okay, so now we can talk about this actual definition of hypercontractivity. And you can think of it geometrically in terms of this L2 ball and L4 balls. So you can define the LP ball by taking all F on the Boolean cube, such that the P norm of F is at most 1, where FP is equal to the expectation of X, of Fx to the P. And it turns out that if we define these LP balls, LP unit balls this way in a probability space, then we get that the L4 ball is contained in the L2 ball. And usually when we talk about operators that are contracting, it means that they send the LP ball to itself. To contract with respect to the LP norm means that you send the LP ball to itself. And this noise operator that we defined earlier, it satisfies a very strong contraction. That's why it's called hypercontractivity, because it sends the large L2 ball into the small L4 ball. So not only does it send the L2 ball to itself, but it actually sends it inside a smaller ball. And for simplicity, I stated here only with respect to 4 norm and 2 norm. So yeah, so it takes the form T-rho F4 norm is at most F2 norm, and it means that you send the large L2 norm into the small L4 norm, L4 ball. Okay, so what are other ways to think about it? Another intuitive way to think about it, about this gap between 4 norms and 2 norms, is to think about peaky distribution versus smooth distributions. So if you have a distribution that's smooth, like distribution of a normal variable, you'll get that the 4 norm is within a constant of the 2 norm. On the other hand, if you take if you take a peaky distribution that takes the value root n with probability 1 over n, you'll get that the 2 norm is 1. Yes, or maybe let's say that x is a random variable that takes the value root n with probability 1 over n, then its 2 norm is going to be 1, but its 4 norm is going to be 1 over n times n squared. So x4 to the 4 is n, and x4 is n to the 1/4. So the 4 norm is much larger than the 2 norm. So the 2 norm is little o of the 4 norm, and that's a behavior that's like a peaky behavior. And the noise operator intuitively it smoothes out the function. It makes it more like this picture, and then it makes the 4 norm within a constant of the 2 norm, and not like the peaky distribution where the 2 norm is little o of the 4 norm. Okay, and it turns out that another equivalent way to think about hypercontractivity is to say that certain functions that are called low degree functions, that they are smooth. So what are these low degree functions? So you have these characters that output 1 if the number of ones in the set S, in the S coordinate is even, and output -1 if the number of ones in the S coordinate is odd. And it turns out that these characters, they form an orthonormal basis, and every function can be written as a linear combination of these characters. And you can take the low degree part of the function to take only the to take of the sum only the set S that have small size, that have size at most D. And this is the degree of F is the largest D for the smallest D for which F is equal to F at most D. And this is the degree of the function as a polynomial in the coordinates. So this is like a natural notion of a degree. And the dictators are functions of degree 1. So if you take the dictator xi, this can be written as -1 to xi +1 over 2, I want to say. So, or maybe it should be something else, but the dictators are a function of degree 1 for that reason. And it turns out that to be a low degree polynomials means to be a low degree multilinear polynomials in the dictators. And another equivalent way to think about the hypercontractivity theorem is about smoothness of low degree functions. So if we take a function that's low degree, like the dictator with probability 1/2 it's equal to 1, with probability 1/2 it's equal to 0, then the 4 norm should be within a constant of the 2 norm. The dictator is of degree 1, so, but in general we have this corollary of hypercontractivity that says that the 4 norm is within a constant of the 2 norm. And the proof is quite simple. It turns out that if you look at this noise operator, it has this this neat Fourier formula where f at s chi s, where we multiply the character chi s by rho to its size, rho to the size of s. And if you take the special case where f is homogeneous of degree d, so f is equal to sum of f at s chi s only over a set of size exactly d, then T rho f is only multiplies the function by a constant to the d. So if we apply the hypercontractivity to get this inequality, we can just obtain that this is just equal to this thing, and then we can so for homogeneous function, this is very easy, and you can actually show it for all functions that the 4 norm is within a constant of the 2 norm. Okay, so let's summarize so far the way to think about hypercontractivity. So one way to think about hypercontractivity is that it sends the L2 ball into the small L4 ball, which is this notion. One consequence of it is the small set expansion theorem that tells you that if you have a small set A and you apply one step of the noisy random walk, then you leave the set with high probability, or you stay in the set with a small probability. And the other way to think about it is about smoothness of low degree functions, which means that if you have a low degree function, it has this smooth behavior, and its 4 norm is within a constant of the 2 norm. So I guess 2 examples to think about are the dictators, fx equal to xi. There the 4 norm is within a constant of the 2 norm. And another function to think about is the function sum of xi over root n. This function has a Gaussian distribution by the central limit theorem, and there also the 4 norm is within a constant of the 2 norm. Okay, and we would like to take this notion of hypercontractivity and to import it into the symmetric group in order to apply it for a product-free sets. So you can sort of see how this notion of small set expansion that we had. Yeah, so this notion of small set expansion, you can sort of see how it's related to mixing, which is what we needed in order to upper bound independent sets in Cayley graphs. And we would like to import it to the symmetric group, and then to the alternating group, and use it to upper bound product-free sets. But before doing that, we can look at this model of Sn. So Sn, we have a much easier model, which is as the product distribution, which is n to the n. So it's like m to the n, but the special case where m is equal to n. And then the symmetric group is a subset of it. It can be thought of as a subset of it. It consists of all vectors, all of whose coordinates are different. And it turns out that when we look at other domains, the only thing that we need to understand in order to do Fourier analysis is what are the dictators. So it turns out once you have dictators, you can talk about hypercontractivity. So what are the dictators in all of these domains? In the Boolean cube, we have the dictator, just fx equal to xi. In the multi-cube, m to the n, we can choose any I in n and j in m, and take the function 1 xi is equal to j. So it corresponds to the set of all vectors whose I coordinate is j. And this is the notion of a dictator in the multi-cube. And we talked about also set systems like the Erdős-Corrado theorem, where a function is a dictator if it contains a given element. So f of a is 1 if a contains I. And we can also define it for permutation. So f of sigma is 1 if sigma sends a given element I to a given element j. Okay, so defining dictators wasn't too hard, and it turns out that once you have dictators, you can talk about hypercontractivity, surprisingly. So how do you do that? Yes, so usually when people talk about Fourier analysis in the symmetric group, they talk about non-abelian Fourier analysis or representation theory, but actually all you need is a dictator to do Fourier analysis or some form of Fourier analysis. So how do you do this Fourier analysis on the other domains? You need dictators to be of degree 1. You need product of d dictators to be of degree d. And linear combinations of products of d dictators should also be of degree d. And once you have that, you can define the space of degree at most d functions to be linear combinations of products of d dictators. This is the space of degree at most d functions. And then the degree of f is the largest d for which you are of degree at most d. So once you have this notion, you can define the notion of the degree, and you can ask whether hypercontractivity is true. So whether the 4 norm of f is at most c to the d times the 2 norm of f, whether we have this smoothness notion, which is essentially equivalent to hypercontractivity. So whether low degree functions are smooth. Okay, and we can ask it in all of these domains, but the problem is that the answer is no. So why is that? The dictators, as we said, have degree 1, and they are Boolean in these domains. And if we take a dictator, it has expectation alpha. and alpha is little o of 1, then we get that the 2 norm is root alpha because f takes Boolean values, and the 4 norm is alpha to the 1/4. So the 2 norm is little o of the 4 norm. And that's bad news for hypercontractivity, because we'd like to say that the 4 norm is within a constant of the 2 norm for degree 1 functions. But dictator, if the dictator is small, then we have no hope of proving hypercontractivity. Okay, so yeah, so let's summarize what we had so far. So we said that many spaces have notions of dictators. And once we have dictators, we can define what are the low degree functions and can finally ask whether hypercontractivity is true, or at least whether low degree functions are smooth. But it turns out that there is a natural abstraction, which are the sparse dictators. So if we have a Boolean dictator that has small expectation, then we have no hope of proving hypercontractivity, because dictators are of degree 1, and the 4 norm is not within a constant of the 2 norm. And the way we solve it is by proving hypercontractivity only for the global functions and not to prove it. So somehow to exclude the dictators when we are proving hypercontractivity, and then we can get an effective version of the hypercontractivity theorem, but not for all functions, but just for the global functions, those functions that don't look like the dictators. Okay. Okay, so I guess I have 2 minutes, so before questions, I assume. So maybe I'll just say quickly. So here we have, so the noise operator can be defined in an analog way to the multicube. And you can show that sparse dictators not only ruin the smoothness of low degree functions, but also ruin small set expansion. And they also ruin hypercontractivity. And then you have to find a way to deal with these sparse dictators. And
you can slow down a little bit. Yeah, it's okay. I mean, yeah. Yeah, we are not in a super rush. So yeah.
Okay. Okay, but anyways, probably it's not a good idea to I just want to outline the thing. Dictators ruin everything, so we don't have so we can define the noise operator in an analog way in the multicube. Okay, maybe so with some probability we forget stuff, with some probability we remember them, and those that we forget we resample, and then we have an analog noise operator. But it turns out that once the sparse dictators ruin everything. So once you have dictators that are small, you have no small set expansion. This is a calculation that you can make. Okay, maybe let's make it. So dictators in the multicube is the set of all vectors whose first coordinate is 1. And then if we choose a random x in A and take a noisy version of x, then the probability that y is in A is at least rho. Because with probability rho, we remember xi. With probability 1 minus rho, we forgot it, but with probability rho, we remembered it. And once x belongs to A, it means that x1 is 1, and therefore also y1 is going to be 1 with probability at least rho. And if we choose rho to be 1/2, it means that we have no small set expansion. So even though the set A is small, when we take a step of the random walk, we stay in the set with high probability. In the Boolean cube, we had the same. It was the same thing, that the probability that y was in A was large, but A wasn't small. So the difference is that the dictators here are sparse. And and you can make calculations that dictators kill hypercontractivity. And the traditional way of dealing with hypercontractivity was to decrease the noise rate. Instead of talking about T rho when rho is a constant, they talked about rho which was very close to 0. And it turns out that such a theorem is not very effective. And another way to deal with it is reverse hypercontractivity. This gives you some of the consequences of hypercontractivity related to mixing, but not all of them. Modified log Sobolev and reverse hypercontractivity are actually the same thing, but the format forced me to have 4 stuff here, so I had put this modified log Sobolev as well. And yeah, hypercontractivity for global function is the new thing, and it's the new way for dealing with these sparse dictators and get basically all the consequences of hypercontractivity for the functions that don't look like dictators. Okay. Okay, so okay, so this is like a messy slide, so maybe I'll just give the notation here. So given a function f and a set s, we can restrict this set s to some coordinate x. So we can define a function on the rest of the coordinates by letting fs of x y be f of x y. Let's say that s is the first t coordinates, and then this notion makes sense. But it makes sense for every subset s of n. Okay, so now we can finally define this notion of globalness. And we say that a function f is epsilon global if the two norm of the restriction of each restriction is small. And this is a notion that holds automatically when we talk about the Boolean cube. It turns out that it holds automatically with epsilon, which is equal to the two norm of f. Which we need to include anyway, because we can also take S to be the empty set. So this means that the two norm of f is small, this notion. So we have two norm of f, this is most epsilon. And then if we take f inside any dictator, so we can take f inside any dictator and look at the two norm. So what's the density of f inside each dictator? This is also small. And but slightly less small, maybe it's at most 100 to the epsilon, 100 times epsilon. And then if we take two coordinate and restrict I to xi and j to xj, so we look in the inside the intersection, we look at f inside the intersection of two dictators, those that send those with ith coordinate is xi and jth coordinate is xj. Then the two norm is at most 100 square times epsilon, and so on. And the larger the set is, the weaker this condition is. We have 100 to the s. So this is a condition about small sets. It tells you that if the density inside small set is inside dictators is small. So this is like, it tells you that you don't behave like a dictator. And the best epsilon you can take is the two norm of f, because this notion in particular requires the two norm of f to be at most epsilon. And the trivial epsilon to take is the infinity norm of f, because you can always take upper bound the two norm by the infinity norm. And the infinity norm is maximized when we don't take restrictions. So this is the trivial one. And it turns out that you get all the consequences of hypercontractivity when we plug in epsilon to be the two norm, and you get something non-trivial whenever epsilon is non-trivial, whenever it's little o of the infinity norm. So what are examples of dictators? So example of global sets. So the dictators are example of global sets. because are examples of sets that are not global. Because if we look inside dictator, the density jumps from being very small to 1. And the examples of random set, example of global sets is the random example. If we take the indicator of a random set, we'll get a global set. And also, if we take a function that's essentially on the Boolean cube, it's also an example of it's also in the Boolean cube, this notion of globalness also holds with the best epsilon, the 2 norm of f, for free. This is easy to verify. And what we prove that once we assume this globalness notion, then we can get all the consequences we want. So if f is epsilon global, then we get this inequality. So if we plug in the 2 norm of f, we get hypercontractivity, and we get this smoothness notion, where when epsilon is the 2 norm of f, we're happy. And it turns out that these notions give you small set expansion once epsilon is non-trivial. So if you want that to say that the probability of returning to a small global set is small, all you need is to have epsilon globalness for epsilon, which is little of 1. Okay, so that's the last slide. So the 2 main points that I wanted to make is that extremal, so Erdős-Corrado type problems appear everywhere. And it turns out that even in problems in additive combinatorics and the group theory, it turns out that dictators appear as extremal examples. So this was like one of the main points. And the other main point was this hypercontractivity tool for global functions. It turns out that this is a powerful tool when we have dictators are sparse. When the dictators are sparse, so this replaces the hypercontractivity that fits in the case where the dictators are dense. Okay, so that's the main point.